So I start by introducing fluidizations. Fluidized beds are widely used in industries for chemical reactions, drying, coating, heating, and cooling. Fluidizations occur when pressurized fluid passes through solid particles, making them behave like a fluid. There are some advantages like high heat and mass transfer rates due to excellent mixings and minimal temperature gradients in reactions. There are also some challenges such as uneven gas-solid contact, vessel erosions, and lastly particle attritions. Filter beds are common in backwashing filters, ion exchange, and chemical reactors, which is industrial relevance. And this experiment focuses on the fluidization behavior of fine sand in a gas-solid system. The objective of this experiment is to study the behavior of fluidization, to analyze the pressure drop versus airflow rate, to identify the fluidization point and its airflow rate, and lastly to calculate the bed void fraction of fine sand. And the scope of this experiment is to investigate the fluidization principles of fine sand using a fluidized bed and to examine how different airflow rates affect bed thickness, bed conditions, and lastly pressure drop across the system.
Let's continue to literature review. Fluidized bed is widely used in chemical processing industry such as separation, rapid mass and heat transfer, and also catalytic reaction. A standard fluidized bed consists of cylindrical column filled with small particles through which a fluid flows. While the fluid is usually a gas, liquids can also be used in some cases. The behavior of particles within the bed is heavily influenced by the velocity of the fluid. At low flow rates, the fluid passes through the spaces between the particles without disturbing them, a state commonly referred as a fixed bed. As the flow rate increases, the drag force may overcome the gravitational forces, leading to particle movement. However, as the bed expands and the fluid velocity decreases within the voids, the drag force also reduces. This results in a dynamic state known as fluidization. At the fluidized point, the pressure drop across the bed solid equals weight or bed solids per unit of surface cross-sectional area. In the early state of fluidization, the equation can be as shown as below, and the particles will not move when a fluid flows through a layer of solid particles at low velocity. So the Ergun equation uses the pressure drop as shown as the equation below. The Ergun equation can also be used to determine the different fluidization types. If laminar flow occurs, it signifies that the gas velocity that exists in extremely small particles is moving at a slow rate, so the formula will be as shown below. However, if the flow is turbulent, which indicates that the movement of small particles is occurring at a high rate and causes floating, then the equation will be as follows.
For the methodology of this experiment, firstly, we observe the thickness of the bed of grains before starting the experiment. Second, the power of the main system is switched on. Next, the experiment started by manipulating the coordinated control valve to 1 to increase the airflow rate to 30.0 m3 per hour. Next, the pressure drop was measured and recorded manually. Then, the thickness of the bed of grains and the behavior of the fluidized beds of grains were observed and recorded after 2 minutes to stabilize the bed. After that, steps 3 to 5 were repeated with the increment of one value of the coordinated control valve until the recorded pressure drop was constant. And finally, the experiment ended by switching off the system.
So after we're done with the experimental itself, we obtain few of the data that can help us with result and discussion. One of it is airflow rate, thickness of the bed of the grain, pressure drop, and lastly, the observation during the experimental. So by using this data, we can come up with the result and discuss what to further understand regarding the experimental itself. So out of all the data we have recorded, airflow rate and also pressure drop will be calculated in a log form. This is simply just we use the log function of airflow rate, the log function and pressure drop, and both of these data will be plotted in a graph so we can find the fluidization point. This is where we are achieving the objective of this experiment itself.
During the experiment, We collected data by varying the airflow rate and measuring the corresponding pressure drop across the bed. Observation of the bed thickness and particle behavior were also recorded. Based on the table, as airflow increased, the sand particle transitioned from a stationary state to vigorous movement. This behavior change was observed at an airflow rate of 122 meter cube per hour, where particle began moving slowly and further increase led to the vigorous movement. As we can see on the table, at 122 meter cube per hour, the particle moves slowly, while at 135.2 meter cube per hour and above, the particle moves vigorously. From the graph, the relationship between airflow rate and pressure drop was plotted on the logarithm scale. The graph shows a steady increase until it reached a plateau, indicating that the graph already reached fluidization point. The fluidization point was identified at a pressure drop of 35.5 mm of water with an airflow rate of 162.2 m3 per hour. Beyond this point, the pressure drop remained relatively constant despite increase in air velocity. For the bed void fraction calculation, the void fraction of the fluidized bed was determined using the formula. By substituting the value from the pressure drop at 38.5 mm of water, particle density of 790 kg per meter cube, the bed height of 0.074 meter, and the air density of 1.1839 kg per meter cube at 25 degrees Celsius, we obtain a bed void fraction of 0.9328. While the experiment successfully demonstrated fluidization behavior, certain inconsistencies were observed due to the measurement error, including the first one is parallax error while measuring bed thickness, second, air bubble trapped in the manometer affecting pressure reading, third, variation in airflow rate leading to inconsistent data point. To enhance the accuracy in future experiment, we recommended to use the following recommendation, which is the first one is aligning the observer eye level with the scale to minimize parallax error. Second is purging the manometer of any trapped air before data collection. The last one is ensuring stable airflow rate before taking the measurement.
In conclusion, the experiment successfully met all of its objectives. We were able to study the behavior of fluidization and analyze the relationship between pressure drop and airflow rate. Secondly, the results show that the pressure drop across the bed increases proportionally with the airflow rate. This indicates a direct correlation between these two variables. Additionally, as airflow rate increased, the thickness of the fluidized beds also increased. At an airflow rate of 122 m3 per hour, we observed that the formation of bubbles on the surface of the sand bed, which is known as effervescence. The fluidization point was determined when the air velocity reached 162.2 m3 per hour, resulting in a pressure drop of 38.5 milliliter of H2O. Lastly, the calculated void fraction of the fluidized bed was 0.9328, reflecting the high porosity of the bed during fluidization.